Hello friends, welcome to the second theory session for T and F block elements. In the previous session we have discussed about the variation in the atomic radii of these elements across the period and also in the series. We have also discussed about their melting and the boiling points, about their atomic volume and also the density. In this session, we are going to discuss about the ionization energy, oxidation states, as these elements, say the D block elements, they show variable oxidation state. So we'll be discussing about the oxidation states of these elements and also the electrode potential, that is the standard electrode potential of these elements. Actually, the variation of these potentials, the standard electrode potentials across the period and also in the series. So let's start our session here. Let's start with the ionization energy. You must be knowing what is ionization energy. It is the amount of energy required to remove the electron from the valence shell of an atom, the outermost electron, and it depends on the factors like size of atom. So we can say that basically it depends upon the effective nuclear charge, ENC, effective nuclear charge. That is the net force of attraction between the nucleus and the outermost electrons. This effective nuclear charge in turn depends upon the size, of course, and also the shielding effect or the screening effect. The more is the screening effect, the less is the effective nuclear charge and less is the ionization energy. Now these elements, they lie between S and P block elements. And we know that across the period in the periodic table, the size of atoms reduces. Right? The effective nuclear charge increases. This is for all the elements. But now for the transition elements. Ionization energy would be more than S block elements and less than P block elements. Or these elements are less electropositive than S block elements and more electropositive than P block elements. See, these are the ionization energies which are given. Right? Now let's go straight to the point about the variation of the ionization energy across the period. So these are the elements of 3D series. You can see the ionization energies. This is scandium for the first electron at 632. Whereas if I talk of chromium, it is coming out to be 652. If it's copper, it's 744. What is suggested by this? The ionization energy for chromium. See, chromium, the configuration is 3D5 and 4s1. 3D5, 4s1. And for manganese, it is 3D5, 4s2. For copper, the configuration is 3D10, 4s1. And for zinc, the configuration is 3D10, 4s2. Now you can see the variation in the ionization energy. Let's take up for chromium only. For the first ionization energy is less. And see, the second ionization energy is very, very high. Why? Because the electron is to be removed from this stable 3D subshell. It is half filled and so it's stable. When I come to manganese, that is from chromium to manganese, see the jump is substantially high. From 652 it is coming out to be 716. This is because the electron is to be removed from the 4s2, that is the 4s subshell, right, which is completely filled. And again, the second ionization energy is again high because the electron is to be removed from the stable orbital. Right? Now students, you can see the difference in the ionization energies. In case of this manganese, what is happening? The second ionization energy is 1513, whereas in case of chromium, it is 1635. The third ionization energy, if I talk of, for chromium, it's 2994, whereas for manganese, it is again high. That is 3258. After the second electron, what has been removed? What is the configuration of manganese became? It becomes 3d5. So the electron now is to be removed from the stable d orbital. In this case, say in the first case, it is removed from the 4s orbital 1 for S2, right? So the ionization energy is more. Again, what is left after removal of one electron is 4s1, one electron in s orbital. So that is also removed. Now what is left here is 3d, d electrons only. So that there is, see the huge jump in ionization energy. It is from 1513 to 3258. Now in case of chromium, for the first removal of the first electron, the ionization energy is not increased to much extent. See, for vanadium, it is 3d4, 4s2. Vanadium at 650 and chromium at 652. Why? Because the increase is not that much. But in case of second ionization energy, the increase is very, very high. Why? Because the electron is removed from the stable 3d orbital, right? And in this case, this from here, the electron is removed from 4s1, then again from 3d5. This 3d5 should be written here. So the jump in ionization energy is very high for when it's from to the second ionization energy. And the third ionization energy, the jump is not that much. Whereas in case of manganese, the jump is very, very high in case of third ionization energy. So students, this fact can be used for answering few questions like why Cr3 plus is stable whereas Mn2 plus is more stable. It can be used for the study of the reduction potentials, right? So in case of chromium, Cr3 plus is more stable. Cr2 plus. See, the variation in the ionization enthalpies in the second and the third ionization enthalpies of chromium and manganese. This is useful in studying their behavior. See, Cr3 plus or say Mn3 plus is a very strong oxidizing agent. I would like to discuss this question here. My question is, Mn3 plus is a strong oxidizing agent. Whereas Cr2 plus is a strong reducing agent. This can be answered from the ionization enthalpy values. See students, I'll also tell you about the standard electrode potentials over here. In case of, let's discuss first this Mn3 plus. In case of this, what is the configuration of say Mn3 plus ion? It will be 3d4, 4s0, right? Now what it can do is, it can easily take up an electron and move to a stable state or change to a stable state. That is Mn2 plus and its configuration will be 3d5, 4s0. So it acts as a strong oxidizing agent. If I'm talking of Cr2 plus ion, what is the configuration of Cr2 plus ion? It is 3d4, right? Now what it tries to do, even if it is attaining one electron, it will move to the 3d5. But if it is losing one electron, Cr2 plus. If it's losing one electron, it will form Cr3 plus ion and a 3d3 configuration. And you must have seen the third ionization energy of chromium. See, this is the third ionization energy of chromium, which is 2994. Right? And it is much less. And if I'm talking of magnesium, the third ionization energy is very, very high. So here you can see, you can write these configurations and see that Mn3 plus is a strong oxidizing agent, whereas Cr2 plus is a strong reducing agent, though their configuration is same. Right? So with the help of ionization energy, we can explain this. If I'm coming to copper, so you can say that which state of manganese is more stable? Its Mn2 plus state of manganese is more stable, whereas Cr3 plus is more stable because the d orbital attains 3 electrons or attains 3 electrons, which is more stable. And also the third ionization energy, that is less in case of chromium. Now if I'm talking of copper, the first ionization energy is less. See, the increase is not much. But the second ionization energy in case of copper is very, very high. Why? Because the electron has to be removed from 3d10. That is the stable configuration, the completely filled configuration. Okay. Likewise, zinc, the ionization energy, the first ionization energy increases. Why? Because the electron is to be removed from 4s2 orbital. The second ionization energy in case of zinc is less. But in case of zinc, the third ionization energy is very, very high. So students, this ionization energy depends upon the configuration also. The stability of these configurations. And if you understand its variation, then you can easily predict which is going to act as an oxidizing agent and which is going to act as a reducing agent. Likewise, if I'm talking of cobalt, CO3 plus. Cobalt, if I'm talking of CO3 plus, what will it be? Will it be an oxidizing agent or a reducing agent? What is the configuration of cobalt? It is 3d74s2. What will be this thing? Cobalt will act as an oxidizing agent. Right? It takes up electrons easily in the aqueous solution. Okay. Likewise, vanadium 2 plus ion, V2 plus. It will be an oxidizing agent or a reducing agent. What is the configuration of vanadium? Vanadium is 3d34s2. Will it be an oxidizing agent or a reducing agent? Vanadium 2 plus acts as a strong reducing agent. So it acts as a strong reducing agent, right? You can see the jump in the ionization energies. It's not that much. It can lose its electron and it acts as a strong reducing agent. More of this, the oxidizing and the reducing tendencies we can also study with the help of standard reduction potential values. Now let's see the factors which are affecting the ionization energy of D block elements across the 3D series. See, these transition metals have got smaller atomic radii as compared to S block elements, right? Also, their nuclear charge is high as compared to S block elements. So their ionization energies are higher than the S block elements. And so I told you that these are less electropositive than S block elements. The ionization energy first increases up to magnesium 25 and then becomes irregular due to irregular trend of atomic size after magnesium 25 in 3D series. See, we have discussed about the trends in atomic radii. What happens? The size decreases till chromium. Then it becomes stable, right? Magnesium, iron, cobalt, and then increases at zinc. Why so? Because of the increase in nuclear charge and increase in shielding effect. Balance each other, and they are making this atomic radii constant. Right? The same nuclear charge is also affecting the ionization energies. See students, this is a trend in the ionization energy values. The ionization energy of 3D series, if I'm talking about, is say it is increasing. There's a huge increase or large increase at manganese. I have told you about this. Increases in iron, and for iron and cobalt, values are almost constant. Decreases at nickel and then again increases at copper. Why this is the trend? See, as we move across the period, what happens? The atomic radii decreases. Or you can see the nuclear charge increases. That will be a better explanation to this. Say on moving from left to right across a period, the nuclear charge increases. The atomic number increases. But say after manganese, what happens? The pairing of electrons starts taking place in the d orbital. Right? See, in a period, the electrons enter in the same shell. Till manganese, the configuration has reached 3d5 4s2. And iron, the configuration is 3d6 4s2. Cobalt, it's 3d7 4s2. Nickel comes out to be 3d8 4s2. Right? Now what happens? The nuclear charge increases, but due to the pairing of electrons in the d orbital, the repulsion, the interelectronic repulsion also increases, which increases the shielding effect. So there are two forces now. One is the nuclear force of attraction, which is due to the nuclear charge, and the second is the shielding effect, which is due to the interelectronic force of repulsion. These two forces, they are balancing each other, right? But still this nuclear charge, it is increasing. You can see that the value of ionization energy at iron and cobalt is almost constant, and it reduces at nickel. Why? See, the value of ionization energy or the atomic radii is the outcome of these two things, that is the nuclear charge and the shielding effect. So these nuclear charge and shielding effect, they counterbalance each other and they are responsible for the ionization energies. Right? Ionization, the variation, they are responsible for the variation of these ionization energies across the period. You can see here the scandium. Then after that, the next element here is 4D series, starts with zirconium. Zirconium, niobium, molybdenum. Then after molybdenum, you have got technetium. So this trend you can see, there is a increase at palladium. Right? It becomes niobium, molybdenum, technetium, ruthenium, and rhenium. Their ionization energies are almost constant. And then there is increase at palladium. Then there is 4D series. Now what happens in the series? The ionization enthalpy, say you can say this is the 3D series, this is the 4D series, and this is the 5D series. The ionization enthalpies of 5D series of elements are much higher than those of 3D and 4D series. You can see it's huge. There is a huge increase in the 5D series. Can you suggest a reason for this? Why there is a huge increase in the ionization energies of the 5D series elements? Say in this case, in the case of this 5D series of elements, in this 5D series, after lanthanum, there are 14 elements in which the electrons enters into the f orbital. So what will be the configuration of hafnium here? The configuration of hafnium will be 4f 14, then is 5D2 and 6S2. Right? This is the configuration of hafnium. Now there are 14 electrons in the f orbital. This, I have told you that the f orbital has got poor shielding effect. Now due to this poor shielding effect of intervening f orbital, what happens? The effective nuclear charge increases. Because there is less shielding effect, the effect of the nuclear charge on the outermost electron increases. That is, the effective nuclear charge increases. Due to this increase in effective nuclear charge, the value of ionization energy increases. Right? So students, this is a very basic concept, but these are the questions which are normally asked. Why the ionization of energy of iridium is very high as compared to palladium? Whereas the difference in the ionization energies between 3D and 4D series is not much. But in case of 4D and 5D series is very high. So you can say that in the 5D series, after lanthanum, there are 14 elements, right? The electron enters into the f orbital. So due to the intervening f orbitals, what happens? The shielding effect decreases. As the shielding effect decreases, the effective nuclear charge increases. When the effective nuclear charge increases, obviously the ionization energy will be increased. Secondly, the question can be from copper also, that why the second ionization energy of copper and chromium is very high. Right? We'll be discussing few more questions related to this, but here I am discussing about the ionization energy only. See here what I have told you. The ionization energy increases due to increase in effective nuclear charge with atomic number at the beginning of the series. Gradually, the shielding effect of the added electrons also increases. That is, the pairing of electrons takes place in the d orbital. The increased effective nuclear charge and shielding effect counterbalance each other. This should be the increased nuclear charge. The increased nuclear charge and shielding effect counterbalance each other. Thus, after first 5 elements, the values of ionization energy becomes regular. We can't say it's constant. Right? There is a regular increase, not very high increase, but it becomes what? Regular. The value of ionization energy gradually increases, or it may also become constant. Say constant for few elements, ferric and cobalt, the ionization energy value was constant. Or it may decrease. See, there was decrease in the ionization energy from cobalt to nickel. So there is irregularity, you can say, in the ionization energy values after first 5 elements. It gradually increases, or it may become constant, and it also decreases. I have shown you the plot graph of it. The first ionization energy of elements of 5D series are much higher than those of 3D and 4D series elements. Why? In the 5D series of transition elements, after lanthanum, the added electrons enter the next inner 4f orbitals. Due to weak shielding effect of 4f electrons, the ionization energy values for 5D series are higher than 3D and 4D series. Thus, a net result of effective nuclear charge and shielding effect favors for predominating trend of effective nuclear charge, and therefore higher ionization energy values are noticed in 5D series of elements. Ionization energy of zinc, cadmium and mercury are abnormally high on the account of greater stability of S subshell. See here, this is the plot. It is increasing gradually with a high increase at manganese, increasing, becoming constant, decreasing, and again increasing. So it becomes irregular after manganese. Okay. In the other series, you can see there is increase, then it becomes constant, increases, and then decreases. Constant, increases, and then decreases. So this is about the trends of ionization energy of transition elements. Now let's see the oxidation states shown by the transition element. Oxidation states. Most of the transition elements exhibit several oxidation states. That is, they show variable valency in their compounds. See some of the common oxidation states. Now here students remember scandium shows +3 oxidation state. Scandium, yttrium, lanthanum. They all show +3 oxidation state. And their compounds are white. They are colorless. Titanium, it shows +2, +3 and +4. Your vanadium shows +2, +3, +4, +5. Chromium can show oxidation state till 6. Manganese shows oxidation state till 7. Right? And then see the decreasing oxidation state. Say across a period, the oxidation state increases and then it decreases. Say for a given series, the highest oxidation state increases with increase in atomic number. It attains a maximum value in the middle and then decreases. Say magnesium in 3D series has got maximum oxidation state. That is +7. Ruthenium in 4D series and osmium in 5D series. They have maximum values for their oxidation states. Okay? And then the oxidation state decreases. Say Ru of 4D series. The oxidation state shown by it is +7. It is 8 actually. Ruthenium shows the oxidation state of +8. That is maximum. +8. And osmium 5D series, it also shows +8 oxidation state. So if you are asked that which are the elements which show maximum oxidation state, it is ruthenium and osmium. Right? So the oxidation state increases till the middle and then it decreases. Like iron shows the oxidation state till +2, +3, +4, +5 and +6. Cobalt shows +2, +3, +4. Now what is the reason behind this? See, pairing of electrons have started. In case of iron, the configuration is 3d64s2. That is, the electrons are paired. Right? There are 4 unpaired electrons and 2 electrons of 4s orbital. So what will be the maximum oxidation state shown by this? 1, 2, 3, 4, 5, 6. That's it. In case of cobalt, there are only 3 unpaired electrons. Right? So it will be 1, 2, 3, 4 and 5. Right? The oxidation state of nickel, it is +4 is maximum. Copper +1 and +2 oxidation state. Now students, here for copper the question arises that though the say Cu+, it should be more stable. It should not form Cu2+. But still Cu2+ is formed. Cu2+, why it should not form? Because the electron is to be removed from the D10. That is the very stable configuration. But Cu2+ exists and it's more stable than Cu+. See, the stability and the reduction potentials, they are determined by many factors. The factors like the hydration energy, the lattice energy, the ionization energy. See, when an ion is formed, there are 3 types of energies involved. First of all, 4 types rather. First of all, the sublimation energy. Then is the ionization energy. Then is the the hydration energy. So copper 2+ ion, as they are smaller in size as compared to copper plus ions, it is cupric ion. and this is cuprous ion. So the size is small. So when the size is small, the hydration energy will be more, which overcomes the high ionization energy. We'll be discussing these things later also. See, I'm trying to just solve the question, see whatever comes in my mind. Right? Whatever is coming to me, I'm trying to solve here. Later, we'll be discussing these things again. The outermost electronic configuration of transition elements is what? The N-1, D 1 to 10 and Ns 1 to 2. Since the energy levels of N-1d and Ns orbitals are quite close to each other, as they belong to the same energy level, both Ns and N-1d electrons are available for chemical bonding. See, the energy levels are the same. Therefore, the number of oxidation states shown by these elements depends upon the number of d electrons it has. Right? Their energies are comparable. So the electrons of d orbital as well as s orbital can be used for chemical bonding. See, for example, titanium. The configuration of titanium is 3d24s2. It may show an oxidation state of +2, that is only s electrons are involved or used in chemical bonding, +3 when one d electron is also used, and +4 when both the d electrons are used. The highest oxidation state which an element of a group of transition elements might show is given by the total number of Ns and N-1d electrons. Say manganese, it shows +7 oxidation state. The configuration of manganese is 3d5,4s2. The relative stability of different oxidation states depends upon the factors such as I've told you, electronic configuration, nature of bonding, stoichiometry, lattice energy, and solvation energy. That is the hydration energy, you can say. If it is any solvent, say if the solvent is water, it is called as hydration energy, and if solvent is any other solvent, that is the organic solvent, the energy released there is called as solvation energy. Right? Say if it's alcohol. This solvates. Right? The molecules are attracted by the cations present in the solution. So the more is the solvation, the more is the solvation energy released. The smaller is the cation, the more it has a tendency to attract the negatively charged species towards itself. See, this oxygen has got lone pair of electrons, right? So the smaller is the cation, the more is its tendency to attract these molecules towards itself. The highest oxidation states are found in fluorides and oxides. Why so? Because fluorine and oxygen are most electronegative elements. The highest oxidation state shown by any transition metal is 8. That is in case of ruthenium and osmium, it's 8. So students, this S and N-1d electrons, these sum up and they show the oxidation state, but only till manganese. After manganese, say if you are talking about iron, about cobalt, about nickel, you can't use this rule. Because then the pairing of electron has started and the number of unpaired electrons available will only be used for combination, right? The transition elements in the +2 and +3 oxidation states mostly form ionic bonds, right? Why they are forming ionic bond? Because the oxidation state is less. And in the compounds of higher oxidation states, the compound formed with fluorine or oxygen, the bonds are essentially covalent. Say for example in this permanganate ion, all the bonds between manganese and oxygen are covalent. Within a group, the maximum oxidation state increases with the atomic number. For example, iron shows the common oxidation state of +2 and +3. But ruthenium and osmium in the same group form the compounds of +4, +6, +8 oxidation states. Though the iron shows it is there that they show the oxidation state of +2, +3, +4. But the +4 compounds are not stable, and the oxidation states in the group increases. In the group form the compounds of +4, +6 and +8. That is ruthenium. It forms the compounds where its oxidation state is +8. Osmium. It can also form the compound with the oxidation state +8. Right? Transition metals, they also form compounds in low oxidation states such as +1 and 0. For example, nickel. Nickel in tetracarbonyl nickel has got 0 oxidation state. Likewise, iron in pentacarbonyl iron has 0 oxidation state. Now let's see the ionization energy and the stability of the oxidation states. Of course, the stability of a particular oxidation state will depend upon the ionization energy also. Say for example, nickel 2+ compounds are found to be thermodynamically more stable than platinum 2+ compounds, whereas platinum 4+ compounds are more stable than nickel 4+ compounds. We can compare the ionization energies. See, this is the 4th ionization energy of nickel. It is very high, 11290. Whereas the 4th ionization energy of platinum is 9360. So platinum 4 compounds can be easily formed. And also platinum 4+ compounds are more stable than nickel 4+ compounds. If I talk of the nickel 2+ and platinum 2+ compounds, the nickel 2+ compounds are thermodynamically more stable. Why? Because the nickel 4+ compounds, their ionization energy is very, very high. That is why nickel 2+ compounds are more stable. And in case of, say, platinum, the relative stability of nickel 2+ relative to platinum 2+. Platinum 2+ compounds are less stable than platinum 4+ compounds. No, the point here is that nickel 2+ are more stable than platinum 2+. Because the 4th ionization energy of nickel is very, very high. Platinum 4+ compounds are more stable than nickel 4+ compounds. The answer is again the same. The 4th ionization energy of nickel is very, very high. Right? The ionization of nickel to nickel 2+ requires lesser energy as compared to the energy required for the formation of Pt2+. It is 2490 and Pt2+ requires 2660. Right? This is the thing. Nickel 2+, it requires 2490, whereas Pt2+, it requires 2660. Therefore, nickel 2+ compounds are thermodynamically more stable than Pt2+ compounds. The formation of Pt4+ requires lesser energy as compared to that required for nickel 4+. Therefore, Pt4+ compounds are more stable than Ni4+ compounds. So, the ionization energies can be compared to find out the stability of the compounds. Right? See, PtCl6 2- complex is known, while the corresponding ion for nickel is not known. In this case, the oxidation state of platinum here is +4. It is +4. But nickel 4+ compounds are not known. Obviously, the ionization energy is very, very high. Right? Whereas in case of Pt2+, the ionization energy is very, very high. Other factors which affect the stability of the compound are, first of all, the enthalpy of sublimation of the metal. See, to change into its ionic form, it should be first melted. Right? The enthalpy of sublimation. Sublimation means when the solid state straight away changes to gaseous phase. That is not melting actually. It is sublimation when the solid state is changing to the gaseous state. Also the lattice and the solvation energies of the compound or ion. Scandium, yttrium, lanthanum, actinium do not show variable valency. This I have already told you. So stability of any ion or formation of a compound of transition element with any oxidation state depends on the ionization energy, depends on the enthalpy of sublimation of the metal, depends on the lattice and the solvation energies of the compound or ion. In case of this nickel and platinum, we have found it with the help of ionization energy only. Right? Now let's see the standard electrode potential. I hope this is enough for the session. In the next session, I'll deal with the standard electrode potentials values. We'll be discussing that in details, and we'll be also discussing about the questions about the reasons for the reduction potentials. I hope you have understood the concepts discussed in this session. Now I'll be concluding the students. Thank you students for listening patiently. Just go through the text so that your concepts are clear. Thank you once again and do have a nice time ahead.